In this part, we'll be looking at one of the important strengthening mechanisms in polycrystalline material, that is grain boundary strengthening. So before going into grain boundary strengthening mechanism, let's understand or let's get introduced to some of the terms. Let's say crystalline materials, we talk about single versus polycrystalline materials. So what is the difference between polycrystalline metal and a single crystal? So when I talk about single crystal, I mean that there are no boundaries or the orientation of that grain is along particular way. In polycrystalline metal, when you talk, that is an aggregate of many single crystals. So most crystalline solids are composed of collection of many small crystals or grains, and such materials are termed as polycrystalline materials. And how they form? So we can see that they form during melting itself. Now we would have seen this image many times. So we have these tiny crystals. I can call it as a single crystal over here. So they form out of the melt and they grow in particular direction, and they grow in this fashion as the solidification continues. And when they grow in particular direction, they will impede each other's growth and they will form boundaries. So you have a grain which will have a particular orientation. So here they are marked with the squares, and you can see that the boundaries between them are marked here, which are called as grain boundaries. So each grain is nothing but a single crystal, and such aggregates of such grains or collection of so many grains, we call it as a polycrystalline material. So we have grain boundaries associated with it here, every grain in this polycrystalline material. Now let's move ahead. So let's understand grain and grain boundaries in more detail. So for many polycrystalline material, the crystallographic orientation of individual grains are totally random. What do I mean by this? So let's say here we have shown an EBSD map for this NaL. So let us write this down. So this is our study which we have carried on nickel aluminide, and we tried to do EBSD studies on this, and you can see that each grain has a particular orientation. So this is an IPF map, that is inverse pole figure map. Maybe you can read more about it when you talk about characterization using EBSD, that is electron scatter diffraction. So these are inverse pole figure maps which shows orientation of each grain. So let's say a red grain here is close to this 001 orientation, or a blue grain here is representing orientation 111. So if I consider all this collection of all these grains, so aggregate of all these grains will have a random orientation, or you can say random, it represents a random texture. So we know that an individual grain behaves anisotropically. So that means it has properties varying with the directions. However, if we consider all these aggregates of these grains, so we can say that this material, the polycrystalline material, behave isotropically. Thus, the magnitude of measured properties is the average of directional values. And when I talk about texture, texture is nothing but a preferential crystallographic orientation of grains. So when I say, if let's say if we have a polycrystalline material, but all grains are oriented towards one particular direction, we call it as a textured material. So when we call a random texture, that means the grains are randomly oriented. And when they are randomly oriented, we'll get properties which are isotropic in nature. And the properties will be always the average of the directional values. Now let's understand what is grain boundary. So here we have shown a micrograph, and you can see these are grains and the boundaries are a black region. So there is a contrast here, and the boundaries are looking black. So we can say that the grain boundary is a region where two grains meet, and these two grains are oriented in a different way. So there will be always a mismatch. So this is a mismatch region. So we have this grain oriented in one particular way, this grain is oriented in another way. So the boundary is a mismatch region within these two grains. So this is called a grain boundary. Now why this grain boundary looks black? So you must be knowing this. So we have this surface, let's say we polish this sample, mirror finish, and then we etch it. Let me write that down. So we etch this surface, and as we know that this region will be of high energy regions, so this will get aged more. So this boundary will get aged more as compared to this part or this surface of the grain. And thus when we have a light falling on these grains, what will happen? So this will get scattered in different directions. So that's why this looks darker as compared to grain surface. So this is in a bright field mode. So let me be very specific. So in microscope, if I'm seeing this in bright field mode, then we see grain boundaries to be dark as compared to the surface of the grains. And there is another mode that is called as dark field mode. You can read about these things. So let's move on. So let's understand grain boundaries in crystalline materials. So we have this grain which is oriented in this particular way, and let's consider another grain which is oriented in this way. Now the boundary between these two grains, which I can say, will be of disturbed bondings. So you can say that these are atoms which are at this boundary. So you can say that the coordination number for this and coordination number of these atoms inside the grain will be different at this location. So at grain boundaries, you will have more broken bonds at the boundaries. And thus this region, that is a mismatch region between these two grains, is called as a grain boundary. So we have this grain boundary region between these two grains. And now in terms of defect, what kind of defect is this? So this is a two-dimensional defect, because if I consider this grain, and when they meet each other, that will be a surface, and surface is 2D. So this will be a two-dimensional defect or a surface defect. And you can say that there are number of broken bonds will be more as compared to inside grains, and thus they will be of high energy. So these regions are of high energy or area of high energies. And the grain boundary energy is measured in terms of millijoules per meter square. So we have grain boundaries which are of high energy as compared to these two grains, which is nothing but a region of mismatch between these two grains which has different orientations. Now let's understand based on the misalignment what I mean by misalignment. Let's say I have this grain and I mark the orientation of this grain in this way, and here in this way, let's say these are some particular planes, another type of planes in this grain. So what's the angle between these? Let's say, let me mark it or let me explain it over. Let's assume that these planes are something called 110 planes, and so in this grain, what are the 110 planes? They will be in this way. Now I measure a misorientation between these two types of planes or two planes in these two grains, and that misorientation is called as angle of misalignment. Similarly, I mark here, so let's say here this is a third grain, so let me mark it over here. So here let's say this is 110 type of plane in this grain, and I try to measure an angle between this 110 type of planes with respect to this grain planes in this grain, and this angle, that is angle of misalignment, distinguishes the grain boundaries in two types. So we have low angle or a small angle grain boundary which has this angle of misalignment is less than 15 degrees, and if it is more than 15 degrees we call such grain boundaries as high angle grain boundaries. So here in this case, so this angle of misalignment, which seems to be, let's consider this to be greater than 15 degrees, so the boundary here we will call it as high angle grain boundary, and the boundary here where the misalignment angle is our misorientation angle is smaller, less than 15 degrees, I call it as low angle grain boundary. So let me write it down here. So this will be low angle grain boundary and this will be high angle grain boundary. And this angle of misalignment is also called as misorientation angle. So some textbook mention it as misorientation angle. So we have two types of boundaries, that is low angle grain boundary and high angle grain boundary. Now, as I mentioned you, we are going to get introduced to one of important strengthening mechanisms in polycrystalline materials, and that kind of strengthening is also called as Hall-Petch strengthening. Let me write it down here. Hall-Petch strengthening. And you must be knowing the reason by now because these two scientists, E.O. Hall and N.G. Petch, work on understanding how the grain size affects the strength of a material. So these are two classic papers in metallurgical engineering, and you will be hearing this Hall-Petch relation or its utility in most of the applications when we try to understand the strength of a material. So these two scientists worked differently. So they worked independently and come up with the same conclusion that the strength of a material, let me write it down here. So strength of a material increases with decrease in grain size. So let's say D will be the grain size. So if I decrease the grain size, the strength of material increases. We'll be looking at why this happens. So with this brief history, I will move ahead. So let's understand this, what is happening. So if I have a different grain size material and I try to understand their engineering stress strain curve or true stress strain curve, here I have plotted sigma versus epsilon, how that will look like. So you have larger grains. Let's say this stress strain curve is a larger grain, and let's assume that for the same strain you need this much stress to deform this larger grain size material. Now let's see, you have a smaller grain size material. So what you can see that the strength has increased for a smaller grain size material. So you see an increase in the strength because of the decrease in the grain size. So let's say for deforming material to the same level, here let me do that. Let's say I deform material to epsilon 1 for both cases, for both the cases. So you need a higher amount of stress. Let's say, let me mark here. So let's say for larger grain size you need sigma L, and smaller grain size you need sigma S. So here sigma S is greater than sigma L. And this increase in strength because of decrease in grain size, and this phenomena is called as Hall-Petch strengthening or grain boundary strengthening, because smaller grains will have large volume fraction of grain boundaries and larger grains will have smaller fraction of grain boundaries. We'll be looking at that also. So why does this strength increase with decrease in grain size? That is a question we have to answer. So let's understand in terms of a dislocation moments. When we talked about dislocations, when we say that something which stops dislocation, spins dislocation, or decrease the dislocation motion, impede the dislocation motion, such kind of mechanism will increase the strength. Now let's look at in terms of a single crystal and polycrystalline material how dislocation moment will occur. Let's consider these are the slip planes in a single crystal, and there will be no grain boundaries here. And in polycrystalline, let's say you have these slip planes and you have this boundary because there is a change in orientation. Now let's say you have a dislocation over here in single crystal, and let's say you apply a stress. So this dislocation will glide and come onto the surface. This is what we have seen. And now let's say in case of polycrystalline material, what will happen? This dislocation will move under the influence of stress and comes across this boundary and it gets stopped over here. And now to cause further deformation, I need more stress to move this dislocation. So anything which stops dislocation or impedes its motion will cause strengthening. However, this strengthening will affect ductility. So if I am stopping the dislocation moment, that means I am decreasing the ductility of material. So I am increasing the strength, but I am at the cost of ductility. So with this single crystalline polycrystalline material, you would have understood that the grain boundary acts as an obstacle for dislocation motion. Now, why does it act as an obstacle? Let's say you have this grain, grain A and grain B. Now you can see that there is a slip plane which is marked here and slip plane which is marked here, and this boundary between these two grain is a grain boundary. Now let's consider this dislocation here, which is on the slip plane, gliding on the slip plane under the influence of stress. Now when it reaches here, what happens? There is a break in the slip plane, so it cannot glide anymore or further in this direction, and it requires more stress, and that will cause strengthening. So a dislocation passing into grain B will have to change its direction of motion. So if it has to go in this plane, it has to change its direction. So increase in crystallographic misorientation. If I increase more misorientation, there will be more resistance for this dislocation which is being offered by this grain boundary. So this atomic disorder at grain boundary region or a discontinue in the slip plane will stop this motion of these dislocations, and thus it causes strengthening in the material. That is why grain boundary or increase in the grain boundaries will lead to strengthening of the material. Now let's look at some of the roles of these grain boundaries in plastic deformation. So here we will be talking in terms of temperature too. So at low temperature, when I say low temperature, that means it is less than 0.5 Tm. That is, Tm is a melting point of an alloy. So temperature which are less than 0.5 Tm of that alloy or a metal is called as low temperature for that material. So let's say aluminium, which has a melting point of 660 degrees Celsius, and nickel, which has a melting point something around 1570 degrees Celsius. So what will be the low temperature? Low temperature for aluminium will be 0.5 of 660 plus 273. So we always do these measurements of temperature in terms of Kelvin. This temperature will be a low temperature for aluminium. Now for nickel, it is very clear, it has very high melting point. So nickel will have a low temperature to be 1570 plus 273. You can check these melting points. I'm just roughly writing it over here. So what is a low temperature for nickel is high temperature for aluminum. So based on its melting point, the low temperature and high temperature are distinguished. Now let's come back to the understanding of grain boundaries or roles of grain boundaries in plastic deformation. So at low temperatures, these grain boundaries acts as a barrier or obstacle to dislocation motion. Dislocation pile up against the grain boundaries. We have seen this, why dislocation gets stopped, because there is a change in the orientation or there is a break in the slip plane. And at high temperature, these grain boundaries gets weaker than the bulk. There can be grain boundary sliding leading to plastic flow, opening of voids along grain boundaries. Grain boundaries can act as a source and sinks for vacancies, that is Nabarro creep. So we'll be discussing all these things when we are discussing about creep. Let me write it over here. So when we are talking about creep, we'll be discussing all these points. For right now, let's say you have two grains with a schematic I'm representing. So let's say you have two grains like this, and you have a grain boundary. These are the grain boundaries. So at low temperature, these GBs will be stronger. The strength of GB will be stronger than, so GB strength, I'm talking about GB strength will be on grain interior. Okay, so we have the strength of grain boundaries are stronger than the grain interior. At high temperatures, the strength of grain boundaries will be smaller than, let me write that down also, at high temperature. grain boundary strength is smaller than the grain interior. Why so? Because there are some mechanisms which comes. So you have void formations, you have vacancy formation along grain boundaries, and you have sliding along grain boundaries, and we'll be looking at that when we discuss about creep in the material. So there is a equicohesive temperature, and there you can see that you have the strength equal. So let me write that down also. So when I talk about equicohesive temperature, so we have grain boundary strength is nearly equal to grain interior, and this is an equicohesive temperature for a material. And this simply comes something around to be 0.5 of melting point of that alloy or a metal. So we can say that for fine grain materials, when this temperature is less than equicohesive temperature, the fine grain materials are stronger than the coarse grain materials. If I have temperature greater than equicohesive temperature, that means grain boundary is weaker. Let me mark it over here. So let us say this is a temperature line. So this is equicohesive temperature, and let's understand with this temperature. Let me mark over here. So let's say this is a temperature line increasing this way. So let's say you have coarse grain material and you have fine grain material. So the strength of this we'll be looking at with respect to equicohesive temperatures, and I can write here that fine grain strength is greater than coarse grain strength at temperatures below equicohesive temperature, and at above equicohesive temperature I can say that coarse grain material will have more strength as compared to fine grain materials. And why is this happening? Because grain boundaries get weaker at high temperatures or higher temperatures higher than equicohesive temperatures. That's the reason we see the change in the strength at equicohesive temperature. So basically you should not use fine grain materials at high temperatures. That is what it means if you want more strength. If you want more strength at room temperature, you can use fine grain materials. Now I'll be looking at why these grain boundaries cause strengthening. And mathematically we'll be looking at some models to derive a relation between strength and the grain size in the next part.